In the previous video, we gave you an overview of the concept of ADAS systems and types of ADAS systems which are commercially implemented in the automobiles till date. Now, in this video, we are going to explain about the components of ADAS systems and how do they actually work. A vehicle needs sensors to replace or augment the senses of the human driver. Our eyes are the main sensors we use to perceive the roads visually when driving. Our ears to detect sirens, honking sounds from other vehicles, railroad crossing warning bells, and more. All of this incoming sensory data is processed by our brains and integrated with our knowledge of the rules of driving so that we can operate the vehicle correctly and react to the unexpected. The ADAS systems need to do the same. Cars are being outfitted with radar, sonar, and LiDAR sensors, getting absolute position data from GPS sensors and inertial data from IME Sensors. The processing computers take in all this information and create outputs to assess the driver or take direct action. General working of ADAS systems. The ADAS systems rely on the data that describes the outside environment of the vehicle. The inputs come from the multiple data sources including automotive imaging, LiDAR, radar, image processing, computer vision, and in-car networking. Other input sources can be vehicle-to-vehicle communication or vehicle-to-infrastructure communication. Let us explore about the sensors used in ADAS in detail. The radar, the sonar, the LiDAR, the vision systems that are image sensors or cameras, GPS or GNSS, navigation systems. Bouncing waves of surrounding objects and then measuring their return times is the main principle of range-finding sensors. The radar uses radio waves, the LiDAR uses light, and the sonar, that are also known as ultrasound or ultrasonic sensors, uses acoustic sound energy. All of these sensing methodologies are being used in various combinations by today's ADAS-equipped vehicles. Coming to the vision systems, the output from multiple cameras pointing in different directions are used to create a three-dimensional model of the vehicle's surroundings. Other than that, it is also used for traffic sign recognition, reading lines and other markings on the road, detecting pedestrians, obstructions, rain detection, and more. It is the richest source of raw data and one of the cheapest sensors. The output of these cameras is fed into the ADAS computer system. These systems are programmed to process the stream of images and identify stop signs. For example, to understand that another vehicle is signaling a right turn and that a traffic light has just turned yellow and more. They are heavily used to detect road markings, which is critical for lane keeping assistance. This is a huge amount of data and processing power, and it's only increasing in the march towards self-driving cars. Radio detection and ranging, shortly radar. In ADAS systems, two basic propagation methods are used, direct propagation and indirect propagation. In both cases, they operate by means of emitting radio frequencies and measuring the propagation time of return reflection, allowing the measurement of distance, size, and relative speed of the objects. Frequency ranging from 24 GHz to 79 GHz are used in radar. Higher frequency also means fast detection. It can see through bad weather and as well as other visibility occlusions. Radar is especially good at detecting metal objects like cars, trucks, and buses. They are essential for collision warning and mitigation, blind spot detection, lane changing assist, parking assistance, adaptive cruise control, and more. Sound navigation and ranging, shortly SONAR, also known as ultrasonic sensors. SONAR sensors generate high-frequency audio of the order 48 kHz, more than twice as a human being hearing range. When instructed by the car's electronic control unit ECU, these sensors emit an ultrasonic burst, and then they listen for the returning reflections from nearby objects. By measuring the reflections of this audio, these sensors can detect objects that are close to the vehicle. Ultrasound sensors are heavily used in backup and detection and self-parking sensors in cars, trucks, and buses. They are located at front, back, and corner of the vehicles. Since the sonar sensors operate by moving air and then acoustic reflections, they are ideal for low-speed applications. Because they are acoustic in nature, ultrasound performance can be degraded by exposure to an extremely noisy environment. Interestingly, the electric car company Tesla invented a way to project ultrasonic sound through metal, allowing them to hide the sensors all over the car and maintain vehicle aesthetics. Light detection and ranging, shortly LiDAR, also known as light radar. The LiDAR sensors send one or more laser beams at a high frequency and use the time of flight principle to measure distances. LiDAR captures high-resolution point cloud of the environment. They can be used for object detection as well as mapping an environment. It uses the same principle of the time-of-flight sensor, but at much longer distances, minimum of 75 meter for near field and 150 to 200 meter for far field. High-end LiDAR sensors rotate, emitting eye-safe laser beams in all directions. And IMU and GPS are also integrated so that the system can measure time taken by the beams to bounce back, factoring in vehicle's displacement during the interim, to construct high-resolution 3D model of the car's surroundings called a point cloud. LiDAR sensors can be equipped with almost 128 lasers inside. The more the sensor, the higher the resolution of the 3D point cloud can be built. LiDAR sensors are typically more expensive than radar because of their relative mechanical complexity. They are increasingly used in conjunction with cameras because LiDAR cannot detect colors, such as the ones on traffic lights, red brake lights, and road signs, nor can they read the text as well as cameras. Cameras can do both of those things, but they require more processing power behind them to perform these tasks. The LiDAR can detect objects with much greater precision than radar or ultrasound sensors. However, their performance can be degraded by the interference from smoke, fog, rain, and other occlusions in the atmosphere. But because they operate independent of ambient light, they are not affected by darkness, shadows, sunlight, or oncoming headlights. Global Navigation Satellite System (GNSS) or GPS. The GPS stands for Global Positioning System. It is a constellation of more than 30 satellites circling the planet. Each satellite emits extremely accurate time and position data continuously. When a receiver gets usable signal from at least 4 satellites, it can triangulate its position. The GPS is not alone. There are multiple constellations of GNSS satellites orbiting the Earth right now, like GLONASS of Russia, Galileo of Europe, Beidou of China. The best GNSS systems have the ability to use 2 or 3 of these constellations. Using multiple frequencies provide best performance and reduces errors caused by the signal delays. Consumer-type GNSS provide accuracy of 1 meter, but for autonomy, centimeter-level accuracy is needed. The accuracy can be improved using regional or local augmentation systems. The GNSS also take helps of inertial measurement unit sensors, that are IME sensors, which are made up of 6 sensors in orthogonal axis, each axis having a gyroscope and an accelerometer. These sensors can sense the change in acceleration in all axes, so when GNSS is not available, it helps track the position of the vehicle till the GNSS is available. Advantages and disadvantages of each of the sensors in ADAS. The vision sensors or cameras can see whether the traffic light is red, green or amber or other colors. They are great at reading signs and seeing lines and other markings, but they are less effective at seeing in the dark or when the atmosphere is dense with fog, rain or snow. They require more processing than LiDAR sensors. The LiDAR sensors are great for seeing in 3D and performs well in dark too, but they can't detect the colors. LiDAR can detect very small objects, but the performance is degraded by smoke, dust and rain in the atmosphere. They require less external processing than camera systems, but they are also more expensive than the vision sensors. The radar can see farther up the road than the other range-finding sensors, which is essential for high-speed driving. They work well in the dark and in when the atmosphere is occluded by rain, dust or fog. They can't make models as precisely as camera systems or LiDARs, or detect very small objects as the other sensors can. The SONAR sensors are excellent at close proximity range finding, such as parking maneuvers, but not good for distance measurements. They can be disturbed by wind noise, so they don't work well at high vehicle speeds. The global navigation satellite systems, combined with frequently updated map database, is essential for navigation, but the raw GNSS accuracy of a meter or more is not sufficient for fully autonomous driving, and without a line of sight to the sky, they cannot navigate at all. The autonomous driving can be achieved by integrating with other sensors, including the IMU, and be augmented with the real-time kinematic systems, satellite-based augmentation systems, and the ground-based augmentation systems. All these sensors complement each other and allow the central processor to create a 3-dimensional model of the environment around the vehicle, and to know where to go and how to get there by following the rules of driving and react to the expected and unexpected situations that happen on every roadway and parking lots. That's all for this video. Stay tuned for more updates.